What's up, everyone? What is up, everyone? Excuse me. Mr. Chung here with notes and lecture for Chapter 6. It will cover problem set 7 and problem set 8 and be the last chapter that we're doing before our second exam. It's a pretty short one, so let's get right to it. All right, so Chapter 6 is all about the periodic table and periodic trends. Now, let's do a little bit of history. Mendeleev created the first periodic table, and he organized that by atomic mass, which is pretty close to the way the modern periodic table is. However, the modern periodic table is not organized by atomic mass. Hopefully you know this already, but the modern periodic table is organized by atomic number. So quick pop quiz. Ask yourself, what does the atomic number represent? Can you remember this? It is from chapter 4. What is that atomic number equal to? Hopefully, you said that it's equal to the number of protons, which is also the same as the number of electrons if the atom is in its base state. All right, so nowadays the periodic table is organized by atomic number, and let's take a look at what that means. Okay, so why is it called the periodic table? Well, that's because elements operate according to periodic law, which means that when you organize the elements in order of increasing atomic number, there is a periodic repetition of their physical and chemical properties. Now, this term period just means having repeating patterns. And you've seen this term period before, right? You have different periods at school, you have different time periods, etc. Okay, so, period means that the different physical and chemical properties are going to be very similar, and you're going to see these patterns emerge as you go through the periodic table. So practically, what that means is that elements are going to have similar physical and chemical properties when they're in the same column. So if you look at the periodic table, if you look at down the columns, all right, all the elements in the same column generally have similar physical and chemical properties. Okay, so let's take a look at the periodic table itself. Now, you should know that like the left side is generally what is considered metals. You see in red here. There are some elements that have metal and non-metal properties, and they are called the metalloids, and then the non-metals are in blue. Now, we'll get more into what that means for bonding and stuff like that in further chapters, but for right now, just remember metals are on the left, metalloids are along this staircase, this bold black line here that kind of separates the metals and the non-metals, and then the non-metals are on the right side, and they're in blue. One thing to point out is that hydrogen, even though it fits or it's on top of this first column here, because if you think to the energy level 1, it only has the s orbital, so hydrogen is a little bit unique. It's the only non-metal that you kind of see on the left side, so that's just kind of something that you should bear in mind. Okay, so hydrogen over here is on the left side. All right. Chapter 6.2. It's useful to look at the electron configurations in groups. I should have said that when I talk about groups, I'm talking about columns. So going down columns, all right? These are all groups, like going down, up and down. Columns are called groups, and periods are going left to right. So those are your rows. Those are called periods. Now, if you look at a group, you will notice patterns in the electron configuration of each of the groups. Now, hopefully you feel comfortable enough with the electron configurations now. I'm not going to go over how I got these. If you're still not sure how to get these electron configurations, well, these are the correct ones, but definitely, get some practice in getting those electron configurations. But let's take a look at the noble gases. So the noble gases are this last column here. Excuse me. Sometimes it's in a different color. It's not a different color in this particular periodic table, but these are the noble gases here. Okay. Now, if you take a look at their electron configurations, starting with neon, notice that their outermost shell, their highest energy level, okay, and by highest energy level, I mean the biggest number here. So for neon, it's 2. For argon, it's 3. For krypton, it's 4. Notice what pattern do you see in that outermost energy level? Okay, hopefully you're seeing that, neon is 2s2, 2p6. Argon is 3s2, 3p6. Krypton is 4s2, 4p6. Now, these outermost energy level electrons, they're called valence electrons. And if you notice, for all the noble gases, they all end in s2p6. The only thing that changes is the number in their energy level. Now, if you go back to the periodic table, take a look. Neon ended in 2s2, 2p6. Notice it's in row 2. Argon ended in 3s2, 3p6. That's in row 3. Krypton ended in 4s2, 4p6. That's in row 4. So take a guess, what would xenon end in? Hopefully you said 5s2, 5p6. Now this is the whole concept of the periodic table. It's happening in periods. It's repeating itself. All right, so 2s2, 2p6, 3s2, 3p6, 4s2, 4p6, 5s2, 5p6. And then you bet it, radon, Rn is 6s2, 6p6. Okay, so I've highlighted the valence electrons here in yellow, and just notice you see this pattern. Okay, one thing that people sometimes say or write, in fact, I should write it in here. All right, NS2, NP6, like the valence electrons are always ending in something S2, something P6. All right, so this is the pattern that we see for all noble gases. They're all going to end in NS2, NP6, where, excuse me, I should write N equals highest energy level. Okay, so all noble gases end in NS2, NP6, where N equals the highest energy level. Now, we can also, what pattern do you see in the noble gas valence electrons? I already talked about that. Now, noble gases are unique because their valence electron shells are completely filled. Okay, so, sorry. Noble gases have their valence electron shells completely filled. And what I mean by that is their s orbitals are filled because s can hold 2 and they have 2 in there. And then their p orbitals, same thing. P can hold up to 6. Well, in the noble gases, it's completely filled. S2, P6. Okay? Let's take a look at a couple other groups, and you're going to see similar patterns. All right? So in group 1A, okay, so, you know what, let me just get a periodic table here. So in group 1A, all right, you are, 1A is right here, okay? And we're going to take a look at 1A, this first column, and then 7A, this second to last column, the one next to noble gases, okay? And you can look at it next to, you can look at it, you know, on your own periodic table or in your book. All right, so 1A, lithium ends 1s2, 2s1. Sodium ends 1s2, 2s2, 2p6, 3s1. And potassium ends 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So again, we're seeing the same pattern. All right. The outermost electrons, okay, the biggest energy level, in lithium's case it's 2, sodium's case it's 3, potassium case it's 4, all right, they're all ending in S1. Okay, same if you look at group 7, okay, fluorine ends in 2s2, 2p6, chlorine ends in 3s2, 3p6, bromine ends in 4s2, 4p, excuse me, I said that all wrong. Fluorine ends in 2s2, 2p5, chlorine ends in 3s2, 3p5, and bromine ends in 4s2, 4p5. Okay, so it's following the pattern. And if you take a look at the periodic table again, all right, look, lithium ends in 1s2, 2s1. Well, where's lithium? It's in row 2, ends in 2s1. Sodium's in row 3, it ends in 3s1. Potassium ends in row 4, it's 4s1. All right, so in the same way I wrote NS2, NP6 for the noble gases, we could do the same for group 1A. Okay, how would you write N something to represent the last shell or the last electrons filled for group 1A? Okay, hopefully you said that you would write NS1. Okay, because group A always ends in NS1. What about group 7A? Right? That's going to always end in NS2, NP5. All right, and so let's take a look at the periodic table again. All right, it's going to end in NS2, NP5, where N is the outermost energy level. Fluorine, it's in row 2. So we put N equals 2, and it ends 2s2, 2p5. Chlorine is in row 3. It ends in 3s2, 3p5. Bromine is in row 4. It ends in 4s2, 4p5. Again, the pattern just keeps repeating itself. All right, in the periodic table, the pattern is just going to keep repeating itself over and over and over again. All right, so last thing, like I said, this is going to be a short lecture. Okay, so periodic trends. Now, not only do the elements in the same group end in the same valence electrons or in the same outermost electrons, but the properties of elements follow distinct patterns as you go across a row, all right, which is also called a period. So if you go left to right across a period, you'll see a pattern. Or if you go down a column, which is known as a group, if you go down, you'll also see patterns and trends for various chemical or atomic properties. Now, you tested that in that gizmo that you did, but let's talk about it a little bit. So there's two main factors we are dealing with here. Number one, you're adding energy levels. Every time you go down a row, like go to a next row, you're going to add an energy level. All right, think about this like the solar system. Whenever you add an energy level, the atom gets bigger. All right, not bigger, excuse me. All right, so as I go down from lithium to sodium, I've added a new energy level 3. When I go from sodium to potassium, I added energy level 4. When I go from from potassium to rubidium, I've added energy level 5. Okay, so I just keep adding energy levels when I go that way. However, if you go across a row, I'm adding protons to the nucleus, but I'm not adding energy levels. You're just adding more protons. Now, see, if we look at sodium's row, we're in energy level 3, but as I go across, I'm just adding more protons, but I'm not adding an actual energy level, like it's not getting bigger like that. And so we will see those two factors come in over and over again here, in case you couldn't read that. But you'll see those factors come in over and over again as we look at these periodic trends. So we're going to take a look at 3 of them. All right, so the first trend we're going to look at is called atomic size. Okay, so atomic size is basically the distance between the center of the nucleus and the outermost electron. All right, and again, refer to your gizmo to see a picture of that. But in general, the atomic size increases down a group and decreases slightly going left to right across a period. So actually, I don't need that periodic table because I have one here. Okay, so as you go down a group, down a column, the atomic size will grow. And if you think about it, this makes sense because as we go down a group, we keep adding energy levels. And so as you're adding energy levels, they're just, it's just getting bigger and bigger, right? So, I added, like here, I'm hydrogen, I only have energy level 1, but then I go to the next one, lithium, I added energy level 2. Then I go to sodium, I've added energy level 3. So I just keep getting bigger and bigger and bigger. Now, the thing that's a little bit harder to understand is as you go across a period, as you go across a row, you'll see here that the atomic size gets smaller as you go across. Now, sometimes that's a little counterintuitive because you think you're getting bigger because you're adding protons, but the question is, why do they keep getting smaller? Well, the answer is here in this little handy-dandy figure here. You're increasing the number of protons in the nucleus, which means you're actually pulling in the electrons tighter because the nucleus is still around the same size, but there's more positive energy or positive charge in that than the electrons that are floating around. They get pulled in a little bit tighter. Okay, I'll say that again. You going across a row, you're still in the same energy level. Like this whole row is still energy level 2. All right, so let's say we start here and we're energy level 2 and my electrons are here. Well, as I go across the row, each successive element adds more protons to the center, which means the center is getting more and more positive. Now, we're not adding an energy level, so as the center gets more and more positive, it's going to pull those electrons closer into the center, which makes the atomic size smaller. Okay? Now, hopefully that makes sense to you. If not, go back, rewind, listen to it again. Okay. But that is why it gets smaller as you go across, because you're not adding an energy level, which makes the thing jump in size, right? You're just adding protons, which makes the charge bigger and pulls everything a little bit tighter. Now, that same concept is going to determine how the other two periodic trends that we're going to look at go. All right, so the next one is ionization energy. Okay, so let's just take a look at the first ionization energy, which is the amount of energy it requires to remove one electron from an atom. So you have an atom and you have electrons around it. How much energy does it take to take one of those electrons and just get rid of it? Okay, now the first ionization energy tends to decrease down a group or increase as you go up a group, and it increases when you go left to right across the period. So let's think about why this is. Well, as you go down a group, what do we say happens to the atomic size? All right, you add energy levels, so the atomic size gets bigger and bigger, which means the electrons that you're trying to pull away, you're always going to pull away the one that's furthest away from the nucleus. Well, it's getting further and further away from the nucleus. It's easier to pull away the further away you get. So it makes sense that the amount of energy you need is highest here at the top, because hydrogen is like real tight. It's like holding its electrons real tight to the nucleus. All right. Whereas francium, which has the lowest ionization energy, it's so big, it's like so far away from the nucleus, it's just really easy to pull that electron away. Now, as you go across the row, it actually takes more and more energy as you go across. Ionization energy increases as you go from lithium to neon. Now, why is that? Well, it's again, remember, the atomic size gets smaller as you go across the row, which means the electrons are getting tighter together, which means it's harder to pull the electron away. Okay? Rewind this and just listen to it over and over again until you understand this concept, because it's the same concept that's determining all three of these periodic trends. Okay? So that one's ionization energy. And the last one that we're going to do is electronegativity. This is the one that was not in the gizmo that you did. Now, electronegativity is basically how tightly does an atom hold on to electrons? All right, so I'm going to ask you guys, how do you think electronegativity would compare to ionization energy? Hopefully you said it'll be the same, because if ionization energy is how much energy I need to pull something away, well then the more energy I need to pull the electron away, that must mean that that atom is more electronegative because it's holding on to its electrons more tightly. All right, so you'll see here the pattern is as you go down, electronegativity decreases, as you go down, electronegativity decreases, because you're adding energy levels, the atom's getting bigger, it's easier or it's harder for the atom to hold on to those electrons, so the electronegativity decreases. But as you go right, again, you're going to see the electronegativity increase, because again, the atom's getting smaller and smaller, which means it's holding onto those electrons tighter, okay, which means those atoms hold onto those electrons tighter. Now, if you have trouble remembering all this for electronegativity, just remember, ignore the noble gases for electronegativity, and then fluorine is the most electronegative element, all right? And these four that I've circled here, nitrogen, oxygen, fluorine, and chlorine, those are actually the four most electronegative elements, okay? Now, this might be a lot to digest the first time you hear it, all right? You really have to kind of review lectures multiple times, review your notes multiple times, go over your problem sets after you've handed them in. All right, go back to them after you've handed it in to see if you understand them. Okay, that is how you will get this stuff kind of stuck in your brain. All right, it's only through repetition and extra study. All right, studying when you don't have homework, that's how you're going to get this stuff. So when you're done with this, I would suggest, turn it off and then come back a day or two later, watch the lecture again and see if you understand it better. I'll repeat one more time. The most important thing is that as you go down the periodic table, you're adding energy levels. And as you go across, you're adding protons. Those two things are what determines all these periodic trends. So once you kind of understand why that happens and why that works, all right, these trends are going to make a lot more sense to you. Okay, so good luck. Please watch this a couple times, then ask me any questions that you have. All right, I'm here to help. This should help you with problem set 7 and problem set 8. Yeah, good luck. All right, hit that like button.